So everyone be safe because the situation is not good, right now the season is
Yes.
changing, so try to be in good shape. uh,
Inshallah. Okay, sir.
uh, 8 students have joined.
Yes.
uh, I think they will join. We will start and they will join soon.
Yeah, Asan, inshallah.
They will join soon. We are studying the Zener diode. So today we'll see some of the you know mathematics of Zener diode. So we'll just have a 5 minutes of recap, so that in the meantime some students will join. So they
Assalamu
will.
alaikum.
Walaikum salam. So basically, we're studying Zener diode. We already told that the Zener diode is basically, you know, from this IV characteristics curves, we can say that this region, where the reverse bias region, and when the reverse bias region, the voltage reaches a particular voltage that is known as Zener voltage, it enters in a different region, that is Zener region or breakdown region. So everybody give your role in the chat box. Everyone give your role and batch also. So that is the from this graph we can see much more closer. My students, these topics are already been done yesterday. I'm just recapping for your reminding you. So you can see that here is the Zener region. When it enters in this region, it acts as a voltage source. We all know that. So Zener, the symbol of the Zener diode is like stem, just a small change in the inside, but all the same. This can give us much more in a closer look. I said that how to identify a diode. In a diode, when you see a strip of black or white, something like that, that is the cathode side, or basically the N side, and the other side is the anode or P. So that was the thing. This diagram was very important. I said that in the Zener diode, the positive cycle, and the positive cycle, the diode acts same as the diode. The Zener diode acts same as diode. In the positive cycle, it just replaces as the zero point 0.7 volt. in the reverse bias condition, normally the Zener diode becomes, you see that normally the Zener diode becomes open circuited in the reverse bias condition. When the Zener diode is reverse bias condition, it becomes open circuit. But when the reverse bias voltage crosses V8, that is the Zener voltage, at that time the Zener diode will become a voltage source. The Zener diode will become a voltage source V8. Okay. So at that time, the Zener diode you can replace the Zener diode as the voltage source Vz when it crosses the Zener voltage. That is the important thing we discussed. We discussed this mathematics. If I'm not wrong, in this mathematics,
Assalamu
basically,
alaikum, sir.
walaikum salam. So in this mathematics, we discussed, everybody give your role in the chat box. That in this system, there is a Zener diode available in the output side, and there is a system available here. And we are told that this is the input, what is a sinusoidal input, the maximum voltage is 60 and 60 in the both positive and negative cycle. So in the Zener diode, the Zener voltage is 20 volt, as we can all can see. So we are told that in the positive cycle, the system should not cross 10, 20 volt, and in the negative cycle, the system should be at 0 voltage. It is told. So let's see how it is, maintained by using a Zener diode. This was a thing. We told that in the last class. Still, I'm just recapping because some of the students might miss. That's why I'm just recapping for 5 or 10 minutes. So see that in the positive cycle, this is plus, this is minus. Okay, this is plus, this is minus. So the current will flow in this direction. So when the current will flow in this direction, this will be plus, this will be minus. So we can easily see that the Zener diode is the reverse bias condition. The Zener diode is the reverse bias condition. So this will be something like open circuit. The Zener diode will be open circuit, my students. But at that time, when it is open circuit, the Zener diode is parallel with system, parallel. So that's why the output voltage will be zero because there is no current. When there is no current, there will be no voltage drop. Okay. So when there is no voltage drop, the output voltage is zero. So it will continue till 20.7 volt because at 20.7 volt, your silicon has zero point 0.7 and Zener diode has 20 volt. When it crosses, because the input voltage is 60 volt, so when it is crosses 20.7 volt, at that time the Zener diode will enter the Zener region. So at that time it will be just a 20 volt voltage source. It will be 20 volt voltage source, and this will be also a zero point 0.7 volt voltage source. So my student, it will be zero point 0.7 volt voltage source. So it will, the Zener diode will be 20 volt voltage source. So at that time the system is, the system is parallel with the Zener diode. So we will get 20 volt in the output. So that was, we already discussed. If you missed this, you just see the video of our previous class because we already thoroughly discussed how it is. Just I'm going a repeat or remind a better way. You see that when the input voltage is 20.7 volt, less than 20.7 volt, you can see that there is no current flow. This is also uh, open circuit, so that in the output we get zero voltage. In the output we get zero voltage. But when it will cross the 20.7 volt, you see the next diagram. Suppose here you can see that uh, the input voltage is 20.7 volt. Now is greater than 20.7 volt. Here the Zener diode becomes a voltage source of 20 volt. I told that when it crosses the Zener voltage, it will transfer, it will become a voltage source, which value will be the Zener voltage. Because here, why the Vz equals to 20? Because it is given. The Zener voltage is given here. So that's why 20 volt, we replace the Zener diode at 20 volt. Now we can see, my student, that in the output, it is parallel with the Zener diode. So the Zener diode voltage is 20 volt. So in the output, we will also get 20 volt. So that was the positive cycle. You can see similarly in the reverse bias or in the reverse condition, my student, it will be minus, it will be plus. So the current will flow in this direction right now, and anti-clockwise direction. The current will flow. So it will be plus, it will be minus. So at that time, it will be open circuited because the silicon diode is now reverse bias condition. It will be open circuited. So when it will be open circuited, there will be no current flow in this circuit. There will be no current flow in this circuit. That's why we will not get the voltage in the output. So output voltage will be zero. That's why you can see that this is the output in the positive cycle, the 20 volt, and then the negative cycle, the output is zero. The 20 volt, and there is some portion, the output is zero because at that time The input voltage is less than 20.7 volt. So that's why at that time the output is 0. And rest of the negative cycle, in the negative cycle, you can see the output is 0 because of the circuit is open circuited. That's why there is no current flow here. And in the system voltage, it is parallel to the Zener diode. That's why there is no current in the output. So that was the 10-minute summary of our last class. I just gave this summary just to remind you all that if some students misses the last class, uh, they can have a small refresh of their mind about our topic. Please, everybody, give your role in the chat box. Some students are missing. Everyone, give your role in your chat box. So today we'll solve three problems regarding Zener diode, regarding three conditions. Okay, three conditions. First, you see that here everything is given. You see that input voltage Vi is given. Uh, then Vi is given. The output resistance RL is given. The another resistance value is given. The Zener diode is given, that is 10 volt. The Zener voltage 10 volt. And PZM. PZM means P means power. ZM means M means maximum. The maximum power, that can be dissipated by this Zener diode, that is 30 milliwatt. The maximum power that can be dissipated by this Zener diode, that is 30 milliwatt. So what was told? It was told that for the Zener diode, determine the VL, the VR, the IZ, the PZ. Okay. You need to find out the voltage across RL, the voltage across R, the current going through the Zener diode, and the power dissipated in the Zener diode. These four things you need to find out. So let's start our problem. So as we all know, my student, as we all know, the Zener diode, if the Zener diode was here, the Zener diode branch and the output branch are parallel. The Zener diode branch and the output branch was parallel. So first of all, we will detect that how much voltage is applied on our Zener diode. The input voltage is 16 volt. We need to check that how much voltage that it is applied on the Zener diode from the 16 volt. We all know that voltage divides across the resistance according to the value of resistance. That is voltage divider rule. Okay. So if we just forget, sometimes for sometimes we forget that there is no Zener voltage. There is no Zener voltage. At that time, there are two resistance. One is R, one is RL. So we can easily say that, or we can easily find out that how much voltage is applied across RL. Because if we can find out the voltage across RL, the voltage will be same across the Zener diode because the two branches are parallel. So that's why you can see that here we have find out the V that is across RL. If you want to find out the resistance across RL, then you have to find like that, the RL divided by the total resistance R plus RL, that is voltage divider rule. You might learn from the circuit course that RL, we need to find out the voltage across RL. So RL will be in the upper side and the total resistance across that will be the lower side into multiplied by total voltage VI. Okay, so you can see that here RL divided by R plus RL into VI. If we give all the value, we get 8.73 voltage. My student, now we can say that the output voltage is 8.73. Okay, the output voltage VL equals to 8.73. If you see 8.73. So we can also tell that as the Zener diode and resistance is parallel, so this 8.73 is also applied in the Zener diode. So now I go to my students and ask them what is the condition will be the Zener diode. My students, can anyone tell what is the condition of the Zener diode? Anyone? Anyone?
Sir,
Eh,
can you repeat the question? You said the situation or of Zener diode, right?
Yes. What is the 8.73 voltage is applied across the Zener diode. We can
Yes.
we find out. So what will be the condition of the Zener diode right now? It
The
is
condition, is it reverse or is it forward, right?
yes, yes, yes.
Right now it's sir, reverse by it's forward bias.
Zener diode is forward bias.
Now, previous it was reverse bias,
Yes.
but right now I think, sir, in my opinion, it's reverse bias. That's all.
Yeah, it is reverse bias. You see that here. This
Yes,
diagram is
it's reverse bias.
clear.
The previous diagram was reverse. Yes, I know that.
It was reverse bias. Okay. And it
Yeah.
is 8.73 voltage is applied across here. So I know that it is reverse bias. So what will be right now condition? Is it has it entered in the Zener region or just like reverse bias?
Oh, right now it's forward bias. General reason.
No. My students, you see that this is reverse bias from the connection. When we find out the voltage 8.73 that is applied across the Zener diode, it did not reach or it did not enter the Zener region. Why? Because let me draw the diagram. This is the suppose this is the reverse bias diagram. So this point, the Zener voltage is 10 volt. So to enter this region, you need at least 10 volt. That is given here. V is equals to 10 volt. At least 10 volt. But in our Zener diode, the applied voltage is 8.73. So that's why it is not entered into the Zener region. So it will be just like open circuit. Now the Zener diode will be open circuit because when it enters the Zener region, at that time it becomes the voltage source.
Okay,
Okay,
sir.
but it did not cross the 10 volt. It did not cross the limit. Am I clear?
Okay,
Yes, sir.
sir.
Yes, sir.
So that's why it is reverse bias, I know. But has it entered the Zener region or not? We need to find
No.
that. We saw that we calculated from the voltage RL. Why we calculated the voltage RL? Because RL and Zener diode are parallel. And we all know that in the parallel branches, the voltage are, what is the voltage condition in the parallel
Same,
branches?
sir.
Same, exact same. So that's why we find out the voltage of RL. So 8.73 is also applied across the Zener diode. So we can say that the Zener diode is not in Zener region. So it will not be the voltage source. It will be like open circuit. Am I clear? So at first you
Yes,
need
sir.
to
Yes,
find out,
sir.
my students,
Yes, sir.
that whether the diode enters the Zener region or not. So that's why we calculated the voltage uh, just to ensure that whether our diode enters, we know that the diode is in the reverse bias. But in the reverse bias, we have two conditions: without Zener region, with Zener region. So we just check that, so it is 8.73, so it is not in the Zener region. That's why it will be normal calculation. So you can say, you can see from here that since the voltage is 8.73, which is less than 10 volt, so diode is in off state, that is not in Zener region. So it will be same like, normal diode condition. There will be no specific, difference between the Zener diode and the normal diode. So we are told to find out VL. We already find out VL, my students. So we got VL equals to 8.73. So
Yes, because of
you
their
can
parallel.
see that the input voltage is VI. Okay. So
Yes.
there are only two places to drop this voltage. One is this resistance, another is this resistance. So what will be the resistance voltage across R? The voltage across R will be VI minus VL. So
VL.
VI minus VL. The input voltage is 16.
VL.
Yes, the VL we just find out. So 16 minus 8.73.
8.73.
The 16 minus 8.73. So what will be the voltage? That will be the 7.227
7.27, sir.
voltage. So that is the VR. So what is the next we need to find out? We need to find out the IZ. As this is open circuit, is there any current flowing? No. The current will be
No,
0.
sir.
You see that the current is
0.
very equals to 0. So when the current equals to
0.
0, we need to find out the power. We all know that power equals to Vz into Iz. Vi, P equals to Vi. We all know the power equals to the multiplications of voltage and current.
Current.
Voltage and current.
Current, sir.
So the V is 10 volt, but there is no current. That's why the power will be also 0, isn't it? Am I
Yes,
clear?
okay, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
It's very easy. It's very easy now. But we
Of
need to
course, sir.
ensure that is my Zener diode is in Zener region or not. That is the main.
Or not.
Yes, that is the main question.
Point.
Yes. So let me clear everything and go to the next. So that what I have just discussed, you can see that from here, that in the diagram that it is 8.73. So that is in not in the Zener position. So if we go to the B part, the same mathematics in the B part, then repeat the whole thing. The RL is 3 kilo ohm. Now we need to replace this 1.2 kilo ohm to 3 kilo ohm, and let's see what happens. Okay, let me check the same process, my students, same process. So we just replace this. And if you find that, you can see that if at the very beginning we will find what is the voltage across the RL. We find the voltage 12 volt. Now what will be the Zener diode now, right now? What will be the condition? My students,
Yes, sir.
now we get the voltage across this 3 ohm, that is 12 volt. Now what will be the Zener diode condition?
Sir, we
Sir,
will.
it exceed the brick diode region, sir. The brick down region.
Yes. Basic,
Crosses. It crosses,
basically
sir.
when we calculate the VL, we get 12 volt, and which is
Yes.
greater than 10 volt,
Yes, sir. Greater than.
so it already reaches in the Zener region. So when it is crosses the
Reason.
Zener
Region, sir.
region, we can replace the Zener diode using a
The source.
source 10
Voltage.
volt. But my students, a very interesting thing now I will tell you, that from the calculations we say that the voltage across this resistance is 12 volt. But when the Zener diode is replaced as the voltage source, the output voltage or the voltage across RL will be 10 volt, because those are parallel lines. In
Yes, the
parallel
parallel is
lines, the voltage are always
same
same.
voltage will. Yes,
So
same
same
voltage will
voltage will be
also
same.
spread.
So it will be when it crosses the 10 volt, it will be on, and the voltage source will be 10 volt. Similarly, the output would be also 10 volt. It will be not 12 volt. Though in the calculations we get 12 volt, but in the output we get 10 volt because the Zener diode is placed here. So that's why you see that VL equals to VZ equals to 10 volt.
Visit.
So what is the voltage of R? It will be the rest of the voltage. From the 16, 10 we
Yes.
get
Minus
across
10.
RL. So the rest of the 6 voltage will be across R. So you see
This
that
resistor
the VR equals to 6 volt.
6.
So you already got this two. So next we need to find out what is the current of this volt of this Zener diode. So you see that we can find out the current of IR. We can also find out the current of IRL.
IL.
Yes, because we got the
Also
voltage,
nice,
we got the
sir.
current, isn't it? So you just find out the IL. We know the voltage, we know the resistance, 3.3 milliohm. IR just replace 6 milliohm. And we all know from the KCL, we all know that incoming current equals to the summation of outgoing current, isn't it? So the RIR is
Yes.
Yes.
going here. It is dividing into two sides. One is IZ, other one is IL,
IL.
isn't it?
So yes, yeah.
Yes,
Yes,
sir.
sir. Yes, sir.
The incoming current in this node, this
Ah,
KCL
is
in
it
this node,
now?
the incoming current is equals to the summation of outgoing current.
Then
Six.
divide to
So basically it will be
6.
IR equals to my student IZ plus I
Minus I.
no plus IL. It will be IZ plus IL. So from here we need to find out IZ because we all know IR, we all know IL already here from these two. We already find out. So it will be IZ. It will be IZ equals to IL minus
IR.
sorry IR minus IL. IR minus IL. So you can see that IZ equals to IR minus IL. So 6 milliampere equals to 3.3 milliampere, which is
2.67.
2.67
2.67. 67, sir.
milliampere. So that's how we get the current. Now
Then
this is
I'm
for
there.
the power. Power. We all know the P equals to VI. What is the voltage of Zener diode? My student. What is the voltage of Zener diode? 10 volt. What is the current? 2.67. Just multiply, you get the power. Yes, in this next diagram, you can see that the VZ equals VZ IZ, the 10 volt into 2.67 milliampere, which is 26.7 milliwatt, which is our given specified that our specification, the limit was 30 milliwatt. We can see that our Zener diode is less than our specification 30 milliwatt. Is it clear, my student? I'm unmuting all my students. Is it clear,
Yes, sir.
everyone? Is there any question till now? Is there any question?
No, sir.
Anyone else? Okay. My students, this type of mathematics, this type of problems, you need to solve by your hand. At that time, it will be much more clear. I'm explaining the basic logic, but you also need to practice in your home. At that time, it will be much more clear for all of you. So let me show one more mathematics. You see that here, what is given? Here it is given. You can see that a network is given, but the interesting thing is that you can see that there is no value of RL. There is no value of RL is given, and it is sign is variable. So when you see a voltage, a resistance, something like that, always remember that a resistance, something like that, an arrow in between. What is that? What is the symbol of this? Student, can anyone tell?
Variable, sir. Variable.
That is variable
Variable
resistor.
resistor.
That is variable resistor. That is not a fixed resistor.
Yes.
So the main task is you need to find out the range of that variable resistance. What is the lower range? What is the upper range? Okay, the range of that variable resistance. So in this question, that is the most important thing we need to find out. Okay, so my student, you can see that input voltage is 50, Zener diode is 10 volt, the Zener region, the IZ in the maximum current, the in the Zener voltage in the Zener diode, it is 32 milliampere. The other resistance is 1 kilo ohm. So those are the information are given here. So what can we do at first?
You have to check the Zener, sir.
Yes,
Zener diode.
yes, you can see that, so here this is
Plus,
already, it is
minus.
reverse biased,
Yes.
already reverse biased. So
Biased.
at first we can, just go for the voltage divider rule, my student. Let me clear all. So in the voltage divider rule, we all know that what is VL equals to VRL divided by
RL plus R
R plus RL, good, R plus RL
times V.
equals to into VI, input
Yes.
voltage, VI. So from this equations, if we just, just cross multiply, we get this equation. Cross multiply and just take common. How? You see that if we just multiply with together, it will be something like that VR, the cross multiply, VR plus VRL. You can do by yourself also. VRL into equals to
V.
what will be there? VIRL. VIRL. So now my student, you just take this VRL into the other side and take common RL. It will be VI minus V. So here we all know that this is the V, which is exactly the same as VZ, because these are the parallel. So that's why here in this equation you can say that the RVZ divided by VI minus VZ. Just one line calculation, you will get this equation, the same. Okay, you just take VRL to the other side, take common RL, and take the factor on the other side. It will be something like that. So from here, if we replace the value, R is 1 ohm, the VZ equals to 10 volt, it is given here, and 50 volt and 10 volt. If we divide, we get that
Yeah, minus
that the Zener diode is in the in the Zener region. We need to consider that because now we need to find out the resistance value, that so that the Zener diode remains in the Zener region. So that's why the 250 ohm is the minimum resistance that will make the Zener diode in the Zener region. The 250 ohm resistance. 250 ohm resistance that will make the Zener diode into the Zener region. Okay. So now
Yes.
my student, if this is the Zener resistance, or the resistance across the VL. So let's find out what is the voltage across the R. The voltage across the R will be 50 minus 10, because 10 is across this Zener diode. So
Yes.
total voltage is
Minus 50.
50.
This
So
will be
50
40.
minus 10 equals to 40. So we got the 40. So we can easily find out the current of this
Yes, IR.
resistance. The VR by RR. VR by R. So 40 by 1K, that is 40
MA.
ampere.
Ambis.
40 milliampere. So my student, one thing we need to find, very important, that when the resistance become large, let me clear. The minimum resistance, this will be the minimum resistance 250 ohm across the RL. The interesting thing is that we need to find out the RL max, the
Yes.
maximum resistance across RL max. So just listen my words carefully, my student. One thing is that always remember current and resistance has inverse relation always. When the resistance is high, the current is low. When the
Yes.
resistance is low, the current
Slow
is
current is high.
high. There's the inverse relation, because so we know that V equals to IR, isn't it? So, so there
Yes.
is the inverse relation. I equals to V by R. So that's why this RL will be maximum when the current entering this RL will be the minimum. So IL will be minimum. So when the IL will be minimum, my students, if you see that this is the node where the IR current is entering, isn't it? The IR current is entering and it has two paths. One is across this path, another one is IL. So when the maximum current will be across the Zener diode, so we can say that the minimum current will go to the RL, isn't it?
Yeah.
Is it
I.
clear? Because
Yes,
there is
sir.
only two paths.
Yes.
When the maximum is going in this direction, so the minimum will go on that direction. So we got the total current 40 ampere, 40 milliampere, and it is given that IZM, the maximum current across the Zener diode, it is 32 milliampere. So we can see that if we just subtract from 40 milliampere to 32, we get the minimum current going through the RL. So that's why it is, IL minimum. The minimum current is 8 milliampere. So the minimum current that is flowing against this RL, that is 8 milliampere. So on that condition, that will be the maximum resistance for RL. We now we can find out, we know the voltage 10 volt. So 10 by 8, we get 1.25 kilo ohm. So that is the maximum resistance, my student, for the RL. Am I clear? Everyone is clear, my
Yes, sir.
students?
Yes, sir.
Okay, you see that now from here. What is the? So we are told to find out the. Okay, so we are told to find out the range of RL resistance. So the minimum is 250, the maximum is 125 or 1.25 kilo ohm. And also the current range. The minimum current is 8 milliampere and the maximum current is 40 milliampere. Why?
40 milliamps.
Can
This is
anyone tell me?
2,4, yes.
Can anyone tell why it is a 40 milliampere, the maximum current? Anyone tell? Why? Anyone tell? Or I should explain? My students, the minimum current we already find out that is 8 milliampere.
8 milliampere.
Why it is the maximum current is 40? Because the input
It
current
was
is 40.
22.
The input current is
Yes.
40 milliampere. So
This is 2 power 4.
we all know
What?
that this is, two-way. So when it will be the maximum? When will be the maximum? When the Zener diode is reverse bias, and at that time there will be no current flow. So the total 40 milliampere current will flow against this resistance. So that's why it is told that the maximum current that is possible in the resistance, that is
Now
40.
or next class.
ادرس اسكهر ادرس حاسكهرتها مو تقل
Yeah,
على
I'm
أدكيس
muted.
على مقطع أكثر.
So that's why it is 40 milliampere, my student. And last but not the least, you can see that what is the maximum power that against the diode. You can say that the maximum voltage is 10 volt and maximum current is 32 milliampere. So the 320 milliwatt, it is the power, maximum power dissipated by the Zener diode. Okay. So this was the overall mathematics. I know I can. I hope that you got the main idea. If you practice by yourself, it will be very easy for you. So today it will be our last. This will be our last example of our diode chapter. From the next class, we will start the transistor, the bipolar junction transistor. So this will be our last. So let's finish it in a well manner. You can say that the question is that determine the range of value of Vi that will maintain the Zener diode on state. So basically the Zener diode in our whole calculation that we will consider the Zener diode is on state. That on means in the Zener region, my student, in the Zener region, not in the forward bias, in the Zener region. But we need to calculate the voltage range, that from which voltage to which voltage our Zener diode remains always on. So that is the main thing we need to calculate. So you see that the resistance is given here, the all the Zener valve voltage is given here, and also the our final the output resistance is also given here. So we go to the next diagram. So at first what we'll do, normally we consider that in the normal conditions we just consider that um, uh, this equation is the same equation, my students, whatever we're doing, this is the voltage divider across the RL. So something like that, the V equals to RL divided by R plus RL, my students, R plus RL into VI. Now everything is given here. We need to find out what is VI. That will be the minimum. So at that time, this will be multiplied with this V and RL divided by the cross multiply. That's why you see that the RL plus R into VZ divided by RL. Why it is VZ? Because we all know that the VL
VL is parallel to.
is parallel. Yes. So
Yes.
now if we just plot all the value, we get the 23.67 voltage that is required, at least the minimum voltage that is required for the Zener diode on operation. Okay, so from small calculations we can easily tell. Now let me check what is the current across the RL. What is the current? We all know the voltage, that is 20 volt, and the resistance is given here. So we can say that the current is just placing the value 16.67 milliampere, my student. Okay, 16.67 milliampere. So that is the current across the resistance RL. And if you check this properly, what will be the maximum current of IR? It is given here. You see that the maximum current across the diode is 60 milliampere. That is the maximum current given here, and we just find out the current RL is 16.6 milliampere. So if we just sum these two, we get the maximum current of IR. You see that we just sum these two value, the 76.67 milliampere, that is the maximum current available in the or provided by the IR. So now we got that. Now we need to find out the maximum voltage drop of IR. Okay, so basically the maximum input voltage, we all know that the input voltage will always dropped into the resistance of the the load. So it will be dropped against R and against these two parallel branch, only one, because those are parallel. That's we consider only one. That's why the IR max into R plus VZ. The VZ is already 20, we know that, and the IR max we find out 76.67, and the volt and the resistance is 0.22 kilo ohm. So if you just sum up everything, we get the 67.8687 voltage. That is the maximum voltage available for the VI. So 23.67 is the minimum voltage, and the 36.87 voltage is the maximum voltage for the input voltage. So that's how we will find out the the range of the input voltage. So you can see also see from here on, this is just the output of, so this is just the output of, voltage. Okay. Okay, my student, that's it for today. Is there any question regarding our mathematics? My student,
No, sir.
any student, any student? Let me unmute all and ask questions. Any student, my student, any questions?
Probably okay.
Amiru, aku dah like it.
Please tell in English, please. My student, please talk in English.
Yes, sir. Sorry, I'm talking with Besson.
Yes, talk
You
in
got it.
English.
The lesson very well, sir. You got it.
So everybody give your role in the chat box. Everyone. Is there any question, my student?
No, sir.
No, sir.
So the Zener Diode will be very important for your final exam. So practice this properly. Okay, I have solved 4 problems. So practice this Zener Diode very properly. Am I clear?
Okay.
Sir.
Okay, so from next class we'll start the transistor or bipolar junction transistor. So till then, let me stop the share. So we have maximum I got 13 to 14 students. So please everybody give your role in the chat box so I can figure it out.
What is my ask is
So if there is no question, you can leave, no problem.
Okay, sir. Thank you.